Long before the first stars, our universe existed in total blackness. This was the cosmic dark age, an ancient era shrouded in profound silence. Unlocking its secrets reveals how everything we know, from the galaxies to the atoms in our bodies, ultimately came to be. By the end of this journey, you will understand the universe's origin story in a completely new way. We will explore how a void of pure darkness gave birth to light, and what mysterious force was silently at work, building the cosmos while it slept. What does a universe without any light feel like to you? We begin with a universe of pure, searing brilliance. In its first moments, all of existence was an unimaginably hot and dense sea of energy, a turbulent ocean where particles and light were locked in a constant, frantic dance. This was not the darkness we think of, but its very opposite, a blinding fireball where photons of light could not travel even a tiny distance without crashing into a free electron. The cosmos was an opaque, glowing fog, a plasma so thick that light was permanently trapped within it. But the universe was expanding, and with that expansion came a great and inevitable cooling. As the temperature plummeted, a monumental shift occurred. The frantic particles began to slow, and for the first time, protons were able to capture electrons, forming the simplest of all atoms, neutral hydrogen. This event, known as recombination, was a cosmic turning point. The free electrons that had once imprisoned light were now bound inside atoms. The fog lifted. The universe, for one brilliant flash, became transparent, but this moment of clarity was fleeting. With the primordial light now free to travel, what remained was a vast, expanding sea of dark, neutral gas. The fires of creation had faded, leaving behind only the cold, simple ingredients for everything to come. The stage was now set, not for a grand spectacle, but for the longest and quietest night the cosmos would ever know. This sudden transparency was a flashbulb moment for the cosmos. For nearly 400,000 years, the universe remained that searing, opaque fog. Then, in a cosmic instant, everything changed. As the expanding universe cooled to a few thousand degrees, a fundamental shift occurred. The frantic electrons, which had been bouncing photons around like pinballs, finally slowed down enough to be captured by protons. They paired up, forming the very first atoms, almost all of them simple, neutral hydrogen. This event is known as recombination. In that moment, the prison walls for light came down. The photons, once trapped, were suddenly set free, streaming across a universe that had, for the first time, become clear. That first burst of liberated light is still traveling today. We can detect it as a faint, cold whisper of microwave radiation that permeates all of space, the cosmic microwave background. This is not just any light. It is the oldest picture we have of the universe, a baby photo taken when it was only 380,000 years old. This fossilized glow is the afterimage of the Big Bang's final fiery flash, the last universal glow before the lights went out for good. It marks the precise end of the universe's violent birth and the beginning of its long, dark sleep. So the lights went out. With that first flash of light now racing into the void, the universe settled into a profound and unprecedented state of rest. This was the cosmic dark age, a deep hibernation that would last for hundreds of millions of years. Picture a cosmos of incredible stillness, an expanse so vast and empty that it defies human comprehension. There were no stars to twinkle, no galaxies to swirl. The universe was a near-perfect blackness, filled almost entirely with a sparse, cooling fog of neutral hydrogen gas. This era earns its name for two powerful reasons. First, it was literally dark, a time before any source of light had ignited. But second, and just as important, it is dark to us. This period is one of the most elusive chapters in cosmic history, a time shrouded in mystery because its primordial hydrogen fog absorbs virtually all the light that could possibly reveal its secrets to our telescopes. We are left peering into a veil, trying to decipher what happened in the quiet before the dawn. This cosmic blackness was far from empty. It was a dynamic, if silent, soup of ingredients waiting for their cue. The most abundant substance was that simple hydrogen gas, a uniform sea of raw potential. But there was another, far more mysterious player in this drama. An invisible form of matter, one that neither emits nor absorbs light, was already at work. We call it dark matter, and its presence was felt only through its gravity. While the hydrogen gas spread out smoothly, dark matter began to clump. Think of it like this. In a perfectly still pond, you could sprinkle fine dust that floats evenly on the surface. But beneath the water, an unseen current is slowly gathering leaves and twigs into dense piles. The dark matter was that underwater current, its gravitational pull silently drawing material together, building an invisible framework in the darkness. This was the cosmic scaffolding, the hidden skeleton upon which the first stars and galaxies would one day be built. Alongside this, the faint, cold whisper of the cosmic microwave background still filled every cubic inch of space, a constant reminder of the universe's fiery birth. This primordial soup, a mixture of dark matter, neutral gas, and fossil light, was the quiet reservoir from which our entire cosmic world would eventually erupt. Gravity was the only artist at work in this dark theater. While the sea of hydrogen gas remained almost perfectly smooth, an invisible force was patiently sculpting the future. That force was dark matter, a substance that does not interact with light in any way, yet whose gravitational pull was slowly, inexorably, gathering the fabric of the cosmos. Think of the early universe as a vast, flat sheet of dough. The Big Bang left behind tiny, random variations in its density, like minuscule bumps and dimples. Dark matter's gravity acted upon these tiny imperfections. Over millions of years, each slight overdensity pulled in more and more dark matter from its surroundings. It was a slow, compounding process where gravity's weak pull steadily built up immense, invisible structures. These gathering pools of dark matter formed what we call halos, vast spherical clouds that acted as deep gravitational wells. They were the hidden foundations of everything to come, the secret blueprints for cities of stars that did not yet exist. And into these wells, the neutral hydrogen gas began to flow. Drawn by the same invisible force, the simple atoms that filled the darkness started to drift toward the densest concentrations of dark matter. The universe was no longer a uniform void. It was becoming a tapestry of immense, invisible structures, with rivers of primordial gas silently streaming into the deepest points of gravity's pull. This was the quiet, patient work that set the stage for a revolution. The dark matter scaffolding was complete, and now it waited, poised to ignite the first cosmic flame. So where did these initial seeds of structure come from? The answer is written in the faint, cold glow of the cosmic microwave background. This ancient light is not perfectly uniform. If you could look closely, you would see it is not a smooth sheet of color but a mottled tapestry of incredibly subtle variations, tiny patches that are ever so slightly warmer or colder than the average. These minute temperature differences correspond directly to minuscule differences in density. They are the fossilized imprints of the universe's very first whispers, quantum fluctuations from the Big Bang itself, stretched to cosmic proportions by a period of hyper-fast expansion called inflation. Think of the surface of a calm lake just as a light rain begins. Each raindrop creates a tiny ripple. In the early universe, these quantum ripples were the raindrops, and the cosmic microwave background is the moment they first touched the water, freezing a snapshot of that initial, gentle disturbance. These tiny ripples, these faint overdensities, were the universe's original blueprints. They were the only instructions gravity needed to begin its work. In a cosmos that was otherwise almost perfectly smooth, these were the precious imperfections, the slight concentrations of matter that would, over the immensity of time, become the foundation for everything. A region with just a few more particles of hydrogen, or a slightly deeper well of dark matter, exerted a tiny bit more gravitational pull than its surroundings. It was a self-reinforcing process. As it pulled in more matter, it grew more massive, and as it grew more massive, its gravitational pull became even stronger. This was the slow, patient mechanism that began to transform a formless sea of gas into a structured cosmos of clumps and filaments. The darkness was no longer uniform. The silent, invisible work of construction had truly begun. This immense quiet makes you wonder, why did the universe wait so long to light its first candle? The simple ingredients were all there: hydrogen gas and the gravitational pull of dark matter. But the recipe for a star demanded more than just raw materials. It required a delicate and slow dance between force and resistance. To ignite, vast clouds of that primordial gas needed to collapse under their own weight, compressing to incredible densities and temperatures at the very hearts of those dark matter halos. The problem was cooling. For a gas cloud to collapse, it must shed its energy. It must lose the heat that creates outward pressure fighting gravity's inward pull. In our modern universe, this is a relatively efficient process. Clouds of gas are filled with dust grains and heavy elements like carbon and oxygen, which radiate heat away easily, allowing the cloud to shrink rapidly. But in the primordial darkness, there were no heavy elements. There was only hydrogen, and hydrogen is a very poor radiator of heat. The only way for these first clouds to cool was through a faint, slow process involving the hydrogen atoms themselves. When an electron inside a hydrogen atom spins in a certain way, it can emit a tiny amount of energy as a specific wavelength of light. This process is incredibly inefficient compared to the cooling methods available today. It was like trying to cool a scorching room by opening a single, tiny window. Gravity had to fight an uphill battle against the persistent pressure of the hot, simple gas. This is the fundamental reason the Dark Age endured for hundreds of millions of years. The universe was filled with the potential for light, but it was trapped, waiting for gravity to slowly, painstakingly, win its war of attrition against the heat. Every future star was a cosmic drama playing out in extreme slow motion, a prolonged gestation where the first nuclear furnaces could only ignite once gravity finally overcame the last vestiges of resisting pressure. So how can we possibly know what happened during this era of total blackness? Without any direct light to observe, we must rely on the power of prediction and digital reconstruction. Scientists build entire universes inside supercomputers, crafting virtual realms governed solely by the laws of physics as we understand them. These are not simple animations. They are complex mathematical engines that simulate the interplay of dark matter's gravity, the flow of neutral hydrogen gas, and the subtle effects of that fading cosmic background radiation. Every single parameter is defined by our best theories, creating a digital lab where the primordial cosmos can be reborn and observed. We feed in the initial conditions from the cosmic microwave background, those tiny ripples that were the universe's only initial instructions. Then we press play, and the simulation runs forward through millions of virtual years. We watch as dark matter condenses into its hidden halos, and we see how streams of primordial gas are pulled into these gravitational wells. The key question these models answer is one of timing and structure. How long did it truly take for the first gas cloud to collapse? What did that very first star look like? Was it a solitary giant, or did many small stars flicker on at once? The simulations let us test these scenarios, revealing that the first stars were likely behemoths, hundreds of times more massive than our Sun, burning ferociously bright and dying young. This virtual window is our only way to witness the cosmic dawn, to see the darkness finally give way to the first brilliant points of light. This faint whisper from the darkness is our most promising key to the past. Astronomers are hunting for a specific signal, a ghostly radio emission with a wavelength of 21 centimeters that was once emitted by the neutral hydrogen gas filling the cosmic dark age. Think of every atom in that vast sea of gas as a tiny radio transmitter, each one capable of broadcasting its own faint story. The signal itself is generated by a subtle flip in the spin of the electron inside a hydrogen atom. This quantum event releases a very specific, very low-energy photon, a whisper of radio static that would have permeated the entire universe back then. The problem is that universe has stretched beyond all recognition. The expansion of space itself has taken that 21-centimeter signal and stretched it, pulling its wavelength out to meters or even tens of meters. It has been redshifted into a faint, deep bass note that is incredibly difficult to separate from the roar of our own modern radio chatter and the natural static of the galaxy. Detecting it is like trying to hear a single, specific note from a symphony that played hundreds of millions of years ago, after the music has traveled across an ocean of time and space. Yet if we can isolate that one note, it would transform our understanding. This signal would not be a single picture, but a dynamic map. By tuning to different wavelengths, which correspond to different epochs in time, we could effectively create a movie of the Dark Age. We could watch the hydrogen gas shift from a smooth, uniform distribution to one clumped around the invisible dark matter scaffolding. We could then witness the dramatic finale, the moment when the first stars and galaxies ignited, their intense ultraviolet radiation burning away the neutral hydrogen and causing the signal to fade. This is the ultimate goal of monumental projects like the Square Kilometer Array, a telescope being built across 2 continents to act as a cosmic ear. Its mission is to listen for this echo of structure being born from pure darkness, offering us a direct glimpse into the universe's most silent and formative chapter. The long silence was finally broken by a violent act of creation. Deep within the densest cores of those primordial gas clouds, gravity at last won its epic struggle. After hundreds of millions of years of patient accumulation, the tipping point was reached. Vast reservoirs of hydrogen, now concentrated at the hearts of the dark matter halos, could no longer support their own immense weight. They began a final, catastrophic collapse. Imagine a skyscraper falling in on itself in utter silence, compressing an entire city's worth of material into a single room. This was the birth of a protostar, a furious, churning sphere of gas heating up under the most extreme pressure. At its center, temperatures soared to millions of degrees, and the chaos of colliding atoms reached a fever pitch. Then the impossible happened. The very nuclei of hydrogen atoms, once repelled by their own positive charges, were forced together with such violence that they fused. In that singular moment, a new process was born in the universe. Nuclear fusion ignited in the core, and the first star turned on. This was not a gentle flicker, but the sudden, brilliant flash of a cosmic beacon, punching through the surrounding fog of neutral hydrogen. These first stars, known to astronomers as population 3 stars, were unlike anything that exists today. They were titans, behemoths that could be hundreds of times more massive than our own sun. They burned at ferocious temperatures, shining with a raw, blistering blue-white light that was millions of times brighter than the sun. Their lives were spectacularly short, burning through their nuclear fuel in only a few million years before exploding in colossal supernova. But in their brief existence, they utterly transformed the cosmos. Their intense ultraviolet radiation began to flood the universe, and this light did something profound. It slammed into the surrounding sea of neutral hydrogen gas, and with enough energy, it ripped the electrons right off the atoms. This process, known as re-ionization, began to tear apart the very fog that had shrouded the universe for so long. The era of total darkness was over. A new, light-filled chapter had begun, one where the universe would slowly become the transparent, structured cosmos we recognize today. The long cosmic night had ended, and the first dawn had arrived, heralded by the explosive birth and death of these solitary, magnificent giants. These first stars were the ultimate pioneers in a virgin cosmos. Without any heavier elements to contaminate their composition, they were pure engines of hydrogen and helium, and this purity allowed them to grow to almost unimaginable scales. A single one of these population 3 stars could contain the mass of 300 of our suns. Their sheer size dictated a ferocious and brilliant life. They burned at temperatures so extreme that they did not just shine. They flooded their surroundings with a torrent of the most energetic form of light, ultraviolet radiation. This radiation was the first true sculptor of the cosmic environment since gravity. Wherever it streamed out from a newborn star, it slammed into the vast, dark ocean of neutral hydrogen gas. Each photon of ultraviolet light carried enough power to violently strip an electron from a hydrogen atom, a process we call ionization. One by one, and then in untold trillions, these atoms were torn apart, their electrons sent flying. The star was essentially burning a hole in the fog. Around each of these stellar titans, a growing bubble of transparent, ionized plasma would form. Within these bubbles, light could travel freely for the first time since the universe's initial flash of transparency. They were the first true clearings in the cosmic forest, lighthouses whose beams were not of visible light, but of transformative energy, punching through the primordial gloom. Yet for all their power, their reign was breathtakingly brief. A star that massive consumes its nuclear fuel at a frantic, desperate rate. Where our sun will burn steadily for billions of years, these giants lived fast and died young, lasting only a few million years before their cores collapsed. Their spectacular deaths in supernova explosions were as consequential as their lives. In these violent final acts, they forged the first heavy elements in the universe, like carbon, oxygen, and iron, and then seeded them out into the void. This enriched the pristine gas, providing the necessary ingredients for the next generation of smaller, longer-lived stars and ultimately for planets and life itself. Their legacy was not just the light that ended the darkness, but the very chemical foundation of our future cosmic home. This monumental clearing of the cosmic fog, known as the Epoch of Re-ionization, was not a single, sudden flash of light. It was a slow, creeping dawn that unfolded over hundreds of millions of years. Across the darkness, the titanic first stars and the earliest, faint galaxies were switching on, each one a lonely beacon in the void. But their collective ultraviolet radiation began to perform a grand, transformative surgery on the fabric of the cosmos itself. Wherever this harsh light touched, it blasted apart the neutral hydrogen atoms, stripping them of their electrons and returning the gas to a transparent, ionized plasma. Think of it like a dense morning fog slowly burning away under a rising sun. At first, only small, isolated bubbles of clarity appeared around the very first stars. But as more stars ignited and the first mini-galaxies began to coalesce, these bubbles grew larger, began to overlap, and eventually merged into vast, clear regions. The universe was slowly being rewired for light, its opacity systematically erased. This was the final act in removing the veil that had shrouded the cosmos since its birth. Once re-ionization was complete, light could travel across billions of light years without being absorbed, a fundamental shift that created the transparent universe our telescopes now explore. We are seeing the distant galaxies we do today precisely because this great clearing happened, allowing their light its epic journey to our eyes. But how do we witness this slow-motion dawn directly? Our most powerful time machine is the James Webb Space Telescope, an instrument engineered to capture the faint, stretched light from the very edge of the observable universe. Its mission is to hunt for the earliest galaxies and brilliant quasars, the very objects that finished the work the first stars began. Each pinpoint of ancient light it collects is a piece of a cosmic detective story, a clue to how the universal fog was burned away. By analyzing this light, astronomers can perform a kind of forensic science. They look for specific telltale signs, like the sharp cutoff of light at certain wavelengths, which indicates that the light has traveled through patches of lingering neutral hydrogen gas. It is like seeing the silhouette of the fog itself against the glow of a distant lighthouse. Piecing together observations from thousands of these early objects allows scientists to map the progress of re-ionization, to understand whether it was a swift process driven by a few colossal sources or a more gradual one powered by countless smaller stars. This observational frontier is our direct window into the universe's final transformation from a dark, opaque sea into the brilliant, structured expanse we call home. While the first stars were brilliant pioneers, they were not the only titans shaping the young cosmos. In the hearts of the earliest galaxies, another kind of monster was awakening, one whose power dwarfed even the mightiest star. These were quasars, the most energetic objects in the universe, fueled by supermassive black holes. A quasar is born when a black hole with the mass of millions or even billions of suns begins to feed. As vast quantities of gas spiral inward in a frantic accretion disk, the material is heated to unimaginable temperatures by friction and gravity, blazing with a light that can outshine an entire galaxy. This was not just starlight, it was a raw, concentrated torrent of energy across the entire spectrum, from X-rays to ultraviolet. And it was this ultraviolet radiation that made quasars master destroyers of the primordial fog. A single, brilliant quasar could act as a universal blowtorch, its radiation reaching out across cosmic distances to ionize hydrogen, gas far beyond the reach of any single star. It could carve out immense, clear bubbles in the neutral hydrogen, creating transparent highways through the darkness and accelerating the process of re-ionization on a colossal scale. These cosmic engines worked in concert with the population of early stars, some clearing their local neighborhoods while others reached out to influence regions millions of light years away. The dawn of light was not a gentle sunrise but a chaotic and patchy illumination, lit by the flash of the first stellar explosions and the relentless, piercing beams of these brilliant, feeding black holes. These brilliant new stars were not destined to shine alone. Across the expanding cosmic landscape, the invisible hand of gravity continued its patient work, drawing these stellar pioneers together. The same dark matter scaffolding that collected the first clouds of gas now began to pull the stars themselves into small, clustered groups. These were the seeds of the very first galaxies, tiny islands of light emerging in a still largely dark sea. They were not the majestic, spinning spirals we picture today. These primordial galaxies were small and ragged, perhaps only a fraction of the size of our Milky Way, looking more like irregular cosmic blobs than the structured pinwheels we know. They were chaotic nurseries where massive stars flared to life and died in violent supernova, their explosions shaking the fragile structures and enriching the surrounding gas with the first heavy elements. Yet within this chaos, a new level of order was being forged. Each of these small galactic building blocks was a crucible, a place where stars could influence one another and where future generations of stars would be born from a richer, more complex mix of elements. This was the universe's next great leap, the moment it began organizing its bright new lights into collectives, setting the stage for the vast cosmic cities that would eventually fill the void. This invisible architecture of dark matter did not simply set the stage and then vanish. It became the permanent, governing force behind galactic evolution. The vast halos that first coalesced in the darkness continued to grow, their immense gravitational pull acting as cosmic anchors. All the normal matter, the stars and the glowing gas we actually see, was merely following the blueprint laid out by this unseen skeleton. Each galaxy we observe today, from a majestic spiral to a giant elliptical, is not floating freely in space. It is nestled at the heart of a far larger, invisible sphere of dark matter, a halo that can extend 10 times farther than the galaxy's visible edge. This dark matter framework dictates a galaxy's very destiny. The size and mass of the halo determine how much gas it can pull in from the cosmic web, setting a ceiling on the galaxy's growth and ultimate size. It acts as a protective shield, too. The halo's gravity holds the galaxy together, preventing its stars from being flung into the void during violent encounters or mergers. Think of a city built within a vast, unseen valley. The shape of the valley dictates where the city can expand, and its walls protect the city from external storms. Dark matter provides that valley for every galaxy in the cosmos. Its influence, first exerted in the total blackness of the Dark Age, remains the primary sculptor of the luminous universe we see around us, a silent partner in every galactic story. The death of a star was the universe's first act of true creation. When those first, colossal population 3 stars reached the end of their brief, fiery lives, their cores collapsed, triggering titanic supernova explosions of almost unimaginable power. These blasts were far more than just a final flash of light. They were cosmic forges. In the heart of that incredible pressure and heat, a miracle occurred. The simple elements of hydrogen and helium, the universe's only building blocks, were fused together into entirely new, heavier substances. For the first time ever, atoms of carbon and oxygen were born. Iron and silicon were forged in the stellar inferno. These were the very first heavy elements in all of existence, and the supernova scattered them like seeds, blasting them out in great, expanding shells of enriched gas. This was the universe's first pollution, a vital contamination of the pristine cosmic environment. Before this moment, the cosmos was a pure but barren sea of hydrogen and helium, incapable of forming a single rock or a living cell. That one change, the introduction of these heavy elements, fundamentally altered everything. The next generation of stars that formed from this enriched gas had access to a much richer palette of ingredients. This allowed them to form with a different structure, often smaller and longer-lived than their massive predecessors. Crucially, the dust and heavier elements swirling around these new stars could begin to clump together, first into rocks, then into asteroids, and eventually into planets. Our own solar system, with its rocky inner worlds, is a direct product of this cycle. Every atom of oxygen you breathe, every particle of carbon in your body, Every piece of iron in your blood was forged in the heart of a long-dead star that lived and died before our sun was even a glimmer in the cosmos. That supernova ash is the raw material of worlds and the absolute prerequisite for life itself. These supernova shockwaves were cosmic demolition crews that immediately began rebuilding. When a star hundreds of times the mass of our sun detonated, it did not simply vanish. It unleashed a spherical wall of energy and matter that raced outwards at a significant fraction of the speed of light. This colossal shockwave plowed into the surrounding reservoirs of pristine hydrogen gas, compressing them with immense force. Think of a snowplow barreling through a field of fresh powder, gathering the snow into dense, heavy piles ahead of its blade. The supernova shockwave acted in the same way, sweeping up vast clouds of gas and crushing them. In these newly compressed regions, gravity suddenly found its job much easier. The gas was already dense, its internal pressure overcome by the external force of the blast. This triggered a cascade of new star formation, a second generation born directly from the ashes of the first. A single, spectacular death could thus give birth to hundreds of new stars, igniting a chain reaction of creation that rippled through the early cosmos. This process fundamentally altered the structure of the first proto-galaxies. Without these explosive triggers, star formation would have remained a slow, solitary affair. But with supernova, it became a self-amplifying communal event. These blasts carved out vast cavities and sculpted the gas within a galaxy, creating intricate structures and accelerating its evolution from a simple blob of light into a more complex and dynamic system. The universe was no longer just making stars, it was building stellar communities, and the blueprints were being drawn by explosions. This cycle of death and rebirth transformed the cosmic landscape from a collection of isolated beacons into a flickering, interconnected network of light, pushing the universe faster and faster toward the brilliant complexity we see today. A living fossil from the dawn of time might be hiding in plain sight. The original stellar titans are gone, but the possibility remains that smaller, slower-burning versions of the very first stars could still be shining today. These would be low-mass population 3 stars, formed from clouds of gas that were just a little too thin to collapse into behemoths. Unlike their massive siblings that exploded after a few million years, a small star formed from pure hydrogen and helium could have a lifespan longer than the current age of the universe. It would still be burning its primordial fuel, a cosmic relic from an era before any planets existed. The hunt is on to find one. Astronomers search the vast, sparse halo of our own Milky Way, a region where ancient stars often reside. They are looking for stars with a unique chemical fingerprint, a complete and total absence of heavy elements. In a universe now polluted by generations of supernova, a star with no iron, no carbon, no oxygen at all would stand out as a stark anomaly. It would be a perfect time capsule, a sample of the universe's original composition locked away in a stellar vault. Discovering just one would be like finding a single, perfectly preserved scroll from a library that burned to the ground millennia ago. It would confirm our theories about the first stars and give us a direct, unaltered look at the pristine ingredients from which everything, including us, was ultimately forged. This awakening, the cosmic dawn, was not a gentle sunrise but a chaotic, brilliant explosion of activity. After its long hibernation, the universe erupted with light and structure, transforming from a formless void into a vibrant cosmic nursery. This era marked the true beginning of the universe as we would recognize it, a time when the first stars and the earliest, faint galaxies began to rapidly assemble. The silent, patient work of dark matter finally paid off, as its invisible scaffolding now supported bustling centers of creation. Imagine countless tiny sparks igniting all across a vast, dark plane, each one a new stellar furnace turning on for the very first time. These were not just isolated points of light anymore. Gravity was now pulling these first stars together into small, clustered groups, the foundational building blocks of the very first galaxies. These primordial galaxies were a far cry from the majestic spirals we see today. They were likely small and irregular, chaotic blobs of light where stars were born and died in frantic succession. The entire cosmos was in a state of furious construction, with the first structures establishing themselves against the fading backdrop of darkness. This dramatic change set the universe on an irreversible path, a journey from simplicity toward the immense complexity of the modern cosmic web. The dawn had broken, and with it came the first hints of the rich tapestry of galaxies, clusters, and superclusters that would eventually fill the void. Capturing a whisper from this ancient darkness is one of astronomy's greatest technical challenges. The signals we are hunting for are not just faint, they have been fundamentally transformed by the expanding universe. That pristine hydrogen, which once emitted a faint radio hum at a wavelength of 21 centimeters, has seen its light stretched to monumental proportions. Over hundreds of millions of years, the expansion of space has pulled this signal, lengthening its waves from centimeters to meters and even tens of meters. This extreme redshift shifts the signal deep into the long wavelength radio part of the spectrum, a region that is notoriously difficult to observe. But the problem is not just a faint, stretched signal. It is a matter of cosmic noise. Our own Milky Way galaxy blasts out a roaring cacophony of radio emissions at these same wavelengths, a brilliant foreground that can be millions of times stronger than the subtle whisper from the dark age. It is like trying to hear the faint sigh of a single person from a mile away, while standing in the front row of a rock concert. To make matters even more complex, every other galaxy and radio source that formed after the Dark Age adds its own voice to this chaotic chorus, creating a layered interference that blankets the entire sky. Isolating the primordial signal requires more than just a powerful telescope. It demands a technological and analytical revolution. We must build radio telescopes in some of the most remote, radio-quiet locations on Earth, places like the deserts of South Africa or the outback of Western Australia. These instruments, such as the future Square Kilometer array, will use thousands of individual antennas spread across vast distances to act as a single, colossal ear. They will gather immense amounts of data, and then sophisticated computer algorithms will work like noise-canceling headphones on a cosmic scale, meticulously subtracting the roar of our galaxy and the chatter of later epochs. The goal is to peel back the layers of time, to isolate that one faint, monotone note that holds the story of the universe's deepest sleep. The ultimate goal of these colossal projects is to weave together two separate stories into one coherent history. The Square Kilometer array will listen for the faint radio hum of hydrogen gas as it slowly gathered around the dark matter scaffolding, a direct acoustic map of the invisible universe. At the same time, the Nancy Grace Roman Space Telescope will act as a powerful eye, peering into the same epoch to capture the first points of visible light as galaxies ignited. By combining these views, we will not just see the result, but witness the process itself. It is the difference between finding an ancient, abandoned city and watching a time lapse of its construction from the first foundation to the final tower. The Roman telescope's wide-field infrared vision is perfectly suited for this hunt. The light from those first galaxies has been stretched by the universe's expansion into the infrared part of the spectrum, and this telescope is built to capture that specific, redshifted glow with incredible clarity. It will find the earliest, faintest assemblies of stars, charting their distribution and numbers, telling us just how many sparks were needed to finally set the cosmic dawn ablaze. This partnership between a giant radio ear and a powerful infrared eye will transform our static picture of the Dark Age into a dynamic movie, revealing not just what was there, but how it all came together. We stand on the brink of turning a theoretical chapter in our cosmic story into observed history, finally witnessing the moment our universe woke up. These lingering questions plunge us into the deepest theoretical puzzles of the early cosmos. We know the first stars eventually formed, but the precise trigger remains elusive. Was it a single critical density threshold that caused a cloud to collapse? Or was it a chain reaction where the death of one massive object set off the birth of the next? The subtle dance between dark matter and normal gas is another profound mystery. We understand gravity drew them together, but did the dark matter's invisible presence somehow nudge the gas, influencing its spin or temperature in ways we haven't yet calculated? These are not just gaps in a timeline, they are tests of our most fundamental physics. The conditions of the Dark Age were so extreme, so unlike anything we can recreate, that this era acts as a natural laboratory for the laws of the universe. Any deviation from our predictions could point toward new, exotic forces or particles that played a role in this silent chapter. Perhaps an unknown type of dark matter particle interacted with itself, or a strange form of energy decayed, providing a crucial burst of heat that helped or hindered the collapse of the first gas clouds. Unraveling these mysteries does more than complete our history book. It challenges and potentially expands our understanding of reality itself, pushing the known laws of physics to their absolute limits. The silent blueprint drafted during the cosmic Dark Age still governs the universe we see today. Every filament of the cosmic web, every vast, empty void, and every clustered supercluster of galaxies traces its lineage back to the subtle gravitational seeds planted in that initial darkness. This is not just ancient history, it is the active foundation of our modern cosmos. The invisible scaffolding of dark matter, which first coalesced over hundreds of millions of years, remains in place. The galaxies we observe now, including our own Milky Way, are simply the visible ornaments hanging on this permanent, unseen framework. The distribution of matter you would see on a map of the universe today, with its great walls and immense empty bubbles, is a direct consequence of how dark matter clumped together before the first star ever shone. This deep connection means that by studying the large-scale structure of the present universe, we are effectively reading a fossil record of the Dark Age itself. The patterns we see are the amplified, evolved version of those first tiny ripples in spacetime. Cosmologists use this profound link to tackle the biggest questions of all. By simulating how those initial conditions set during the Dark Age evolve over billions of years, they can test our most fundamental models of the cosmos. They can refine our understanding of the universe's composition, how much of it is dark matter and dark energy. They can better predict the ultimate fate of everything, whether the universe will expand forever into a cold, dark emptiness or eventually collapse back on itself. So when we look at a deep field image from the James Webb Space Telescope filled with countless galaxies, we are not just looking at a beautiful picture. We are witnessing the mature outcome of a process that began in total blackness, a cosmic destiny set in motion long before light itself was born. Our own galactic neighborhood holds ancient relics from that first dawn. Scattered throughout the vast, sparse halo of the Milky Way are stars that have been shining for over 13 billion years. They are the survivors, the second generation that formed directly from the ashes of those first, spectacular supernova explosions. To an astronomer, these stars are not just points of light, they are living fossils. Their chemical composition is a permanent record of the environment in which they were born. The key is to find stars that are incredibly metal poor. In astronomy, any element heavier than helium is called a metal. A star with almost no metals in its atmosphere must have formed very early from gas that was only lightly polluted by the very first supernova. By measuring the precise amounts of elements like carbon, oxygen, and iron in these ancient suns, stellar archaeologists can work backwards. It is like analyzing the chemical signature of ash to determine the type of wood that burned. If a star shows a specific, odd pattern, for instance, a lot of carbon but very little iron, it tells a story. It suggests that the supernova that enriched its birth cloud came from a single, colossal star that died in a particular way, perhaps a pair instability supernova that utterly vaporized itself. Each of these ancient stars is a time capsule, preserving a unique chemical fingerprint that points back to the properties and the deaths of the very first stellar generation. This painstaking work, star by star, allows us to reconstruct the lives of the pioneers we can never see directly, piecing together the legacy of the giants that ended the universal night. This intergalactic medium is a ghostly echo of that ancient era. It is the incredibly sparse gas that fills the vast voids between galaxies, a relic that still remembers the long cosmic night and the violent dawn that followed. To study it, astronomers use one of the universe's most powerful tools, distant quasars. Think of a quasar as a brilliant, distant lighthouse shining through a cosmic fog. As its light travels across billions of light-years toward Earth, it passes through countless filaments and clouds of this intergalactic gas. The gas does not emit its own light, but it leaves a distinct fingerprint on the quasar's light. Specific wavelengths are absorbed, creating a unique pattern of dark lines in the quasar's spectrum, like a barcode. Each set of lines corresponds to a different element and a different level of ionization, telling scientists the composition, temperature, and density of the gas at a specific point along the line of sight. By analyzing the intricate patterns in these absorption lines from many different quasars, researchers can assemble a three-dimensional map of this invisible medium. They can trace how the gas became progressively more ionized and heated over billions of years, directly witnessing the aftermath of the first stars and galaxies as they burned away the primordial fog. This tenuous gas is not just empty space, it is a living archive, a permanent record of the universe's greatest transformation, from a sea of darkness into a tapestry of light. These digital universes are born from a set of simple yet profound starting rules. Scientists program supercomputers with the known laws of physics, seeding a virtual void with the faint density ripples we observe in the cosmic microwave background. Then they set the simulation in motion, watching as gravity begins its patient work on both dark matter and gas. The true challenge emerges when the first pockets of gas become dense enough to collapse. The software must now solve an incredibly complex dance of competing forces. It must track the simple chemistry of primordial hydrogen, calculating how this gas cools by emitting its faint, specific radiation. It must model how the gas fragments as it spins and falls into the deepening gravitational well of a dark matter halo. And crucially, it must account for the star's own feedback on its environment. The moment a protostar ignites, it floods its birth cloud with intense radiation, which pushes back against the infalling gas, effectively limiting the star's own growth. Capturing this delicate balance between collapse and resistance is what makes the simulation so difficult and so vital. Without it, the model would simply create an unrealistically massive ball of gas. The result of this computational ballet is a breathtaking visualization. We do not just see a data plot, we watch a cosmic drama unfold. A dark matter halo emerges as a faint, shimmering web. Rivers of hydrogen gas, represented in glowing blue tendrils, flow inward along these invisible filaments. At the center, a knot of material grows brighter and hotter, churning violently until a point of blinding white light erupts, signifying the birth of the first star. These are not mere animations, they are calculated predictions, allowing us to witness events that no telescope will ever see directly. They show us that the first stars were likely born in isolation, one magnificent giant per dark matter halo, its brilliant life and violent death predetermined by the strict physics of a universe just learning how to shine. This entire cosmic story unfolds on a timeline of almost unimaginable scale. To truly grasp the significance of the Dark Age, we must see it as one essential chapter in the grand biography of the universe. The journey begins with the hot Big Bang, the moment of origin for space, time, and all matter. From that initial state of incredible density and heat, the universe expanded and cooled for nearly 400,000 years, leading to the next pivotal event, recombination. This was when the first atoms formed, setting the primordial light free and creating the cosmic microwave background, that fossilized snapshot of the infant cosmos. And then the lights went out. The long cosmic dark age began, a profound silence lasting for hundreds of millions of years where the universe was a dark, neutral sea of hydrogen, its structure silently being woven by dark matter. This quiet gestation was absolutely necessary, a period of patient preparation. Without it, the next act could never have commenced. That act was the cosmic dawn, the glorious and violent ignition of the very first stars, which ended the darkness and began flooding the cosmos with new light. Their intense radiation then initiated the Epoch of Re-ionization, a slow, cosmic-scale process that burned away the primordial fog and made the universe transparent once again, this time for good. From that point on, the path was set for the full formation of galaxies, their mergers and growth, and the eventual emergence of the complex cosmic web we observe today, leading directly to our own place in a modern galaxy. When you place the Dark Age on this vast timeline, its role becomes crystal clear. It was not a passive emptiness, but a crucial, formative period of incubation. It was the quiet night during which the seeds of everything, from the smallest star to the largest galaxy cluster, were carefully sown, setting the stage for the brilliant and structured universe we are now privileged to explore. This cosmic story of darkness before light feels strangely familiar. Our oldest human myths often begin in a formless void, a primordial chaos that precedes all creation. The ancient Greeks spoke of chaos, a yawning gap from which the world emerged. In Mesopotamian epics, the universe started as a dark, watery abyss. The Maori of New Zealand tell of a deep, unbroken night before the sky and earth were forced apart. These are not mere coincidences of imagination. They are a profound, almost instinctual reflection of a truth now written in the equations of physics. We have always sensed that our origins lie in the dark. The scientific narrative of the cosmic dark age gives this ancient intuition a breathtaking new dimension. It is no longer just a poetic metaphor, but a physical reality. Our universe did indeed begin in a kind of structured chaos, a sea of potential waiting in the silence. The emergence of the first stars is the scientific counterpart to the moment a divine word is spoken, or a great light is kindled, bringing order and life to the formless deep. This connection transforms our understanding of myth. It suggests that for millennia, humanity has been telling a version of the true cosmic story, a deep memory of our universal lineage encoded in our collective consciousness. It invites a humbling perspective. We often see ourselves as the pinnacle of creation, but this timeline tells a different story. human civilization occupies less than a fleeting second on the cosmic calendar. For nearly all of cosmic history, the universe existed in total blackness, utterly unaware that life and mind would one day arise to ponder it. We are the latecomers, the products of an ancient, patient process that favored darkness long before it ever crafted light. Our very existence is a testament to that long, silent gestation. Every atom in our bodies was forged in the heart of a star that itself was born from the dark, primordial hydrogen of that age. We are not just living in the universe, we are literal pieces of it, stardust that has awoken to contemplate its own incredible origins. This realization bridges the gap between the scientific and the spiritual, inviting us to see our search for meaning not as separate from cosmology, but as an essential part of the universe's own long, slow awakening. This long cosmic silence was not a meaningless void, but a critical setup for our own existence. The precise conditions of the Dark Age were a delicate calibration, a necessary prelude to a universe that could one day support life. Consider the timing. If the first stars had ignited too quickly, the universe would have been much smaller and denser. The earliest galaxies would have collided and merged with ferocious frequency, creating chaotic environments where stable solar systems and habitable planets would struggle to form. Conversely, if star formation had been delayed for too long, the expansion of the universe would have diluted the primordial gas to such an extent that galaxies might never have coalesced at all. We would be left with a vast, eternal darkness, devoid of the islands of light necessary for life. The behavior of dark matter was equally crucial. Its unique nature, interacting only through gravity, allowed it to clump into stable halos without dissipating or collapsing. If dark matter had interacted more strongly with normal matter or with itself, it could have heated the gas, preventing it from cooling and collapsing into stars. Or it might have formed overly dense, short-lived structures that would have disrupted the gentle, patient assembly of galaxies. The entire cosmic narrative, from the first hydrogen atom to the complex chemistry of life, hinges on the specific physics that govern that dark, quiet era. This idea connects to a profound concept known as the anthropic principle. In its simplest form, it suggests that the universe we observe must be compatible with the existence of observers. We can only be here to study the cosmos because its fundamental parameters, from the strength of gravity to the density of dark matter, fell within a razor-thin range that permitted our eventual evolution. The Dark Age is a cornerstone of this fine-tuning. It was the universe holding its breath, ensuring that the first steps of structure formation happened in just the right way, at just the right pace, to set the stage for everything that followed. Without that specific long night, there would be no planets, no heavy elements for rocky worlds, and no stable, long-lived stars like our Sun to provide energy for billions of years. The darkness was not an empty intermission. It was the essential backstage preparation for the main event, the silent, patient architect of a cosmos that could eventually become aware of itself. This silent chapter of cosmic history is now stepping into the light of public imagination. Planetariums around the world are transforming these abstract concepts into breathtaking sensory experiences. Beneath their vast domes, audiences are transported into the heart of the primordial darkness, watching as supercomputer visualizations bring the invisible to life. They see the ghostly blue tendrils of hydrogen gas flow along the dark matter scaffolding, and they gasp as the first star erupts in a blaze of brilliant white, its light finally punching through the endless night. These are not dry lectures, they are journeys back in time, crafted to evoke the same sense of wonder that drives the scientists themselves. Documentaries build on this foundation, weaving state-of-the-art animations with the passionate insights of researchers on the front lines of discovery. They frame the Dark Age not as a sterile academic topic, but as the universe's greatest origin story, a detective saga spanning billions of years. The most powerful tools, however, are often the most personal. Interactive websites and museum exhibits allow you to become the cosmic architect. You can adjust the density of dark matter in a simulation and watch how it changes